top. And you know, these would be like civil engineering firms or mechanical engineering firms. And they all said pretty much the same thing. Well, we don't send anybody into space. And I thought, well, there's a lot of things that a person can do when you graduate from a degree in aerospace engineering. So for instance, you need some chemistry, and you take some physics, and you take some civil engineering classes. So there's statics, that's sort of the study of things that don't move when you put forces on them. And then there's dynamics, which is what happens when you put forces on things that are moving. And then strength of materials is a study of how these objects, whether they're moving or not moving, how do they bend and stretch and eventually break, and how do you avoid that? So it's the study of materials. There's lots of math through differential equations, which here is, I think, math 256.
Is that it?
Pardon me?
That's it?
Yeah, well, when I went through aerospace, I thought, man, I got some math. I know math. And then when I went back to school into a math program, it turns out I didn't know so much math. There's a lot more math. But for an engineering major, that was as far as pure math as you had to go. Now, there were other courses, AME, aerospace and mechanical courses, specific to the college. And they were math courses, but they were very specific to engineering and whatever subjects they were talking about in that class. So there was gas dynamics with math for gas dynamics and such like that. So here, gas dynamics and fluid mechanics. All of these classes, they had math in them, math very specific to these fields, but they weren't called math classes. So I wanted to show you some typical things that are being studied at the moment. For instance, here is a microfluidic device for antibiotic susceptibility testing. A nano-engineered biosensor for the rapid detection of biomolecules. So this is what the aerospace department is doing now, in addition to just general fluid mechanics and things that you would expect. But here are some little research topics that you might not expect. My favorite one was this one, the development of software for a portable knee load sensor. Who would have thought that?
Very specific.
Yeah, oh, incredibly specific, yeah. What I realized, though, is that, you know, when you go into math or engineering or any field that has mathematics behind it. For instance, I wanted to study architecture when I was really little. And everybody told me, oh, you're going to need a lot of math. Oh, the math, right? And so I just started taking math classes because I was going into architecture anyway, and you needed the math. But the truth is, you don't need math at all. Zero math to try to design things that fly. A lot of people try to design things that fly without math. Here's one of them. His name was King, I don't know how to say it exactly, Bladed or Bladed. He was a legendary king of the Britons. He is said to have constructed wings for himself without any math. And he tried to fly from the Temple of Apollo to London, apparently. And he got killed when he fell down and broke his neck. So really, that's the problem. It's not that you need math to fly. When you strap those wings on, nobody from anywhere comes around and asks you, do you have your math license? Right? Have you done any math? But the point is, you only live once. And if you go and put a pair of wings on and jump off and you're wrong, that was your last chance, right? And if you go to someone else and try to get this thing funded, you know, you could try 1,000 times. This time I'll paint it brown. This time I'll do it at daytime. Well, who knows what you're going to do next to make sure that, or to see if it's going to fly. But eventually whoever's sponsoring your project is going to say, how much is this going to cost me? How long are you going to be doing this? Right? And so eventually, if you can plan out what's going to happen before you actually jump off that wall, that's where you need the math. And so that's when people started finding success, is when they were trying to write things down, make a picture before you try to build it. How is this thing going to work? How is it going to fit? So one of the people that first tried making models was this guy. Well, I don't know what happened to this guy. There was a lot of people that tried experiments. So maybe he made some drawings, I'm not sure. The look on his face says, I don't know, I don't think he made it. If he had, we might see more flying machines like that. let's see. In here somewhere there was supposed to be a picture of Leonardo da Vinci. There it is. So here's a drawing. I don't know if you can see it very well, but it's one of his early drawings, and he's basically looked at some birds or bats, and he's tried to draw what one of the wings might look like, and some of the structure beneath the wing. And down here are some little drawings of how this person might put it on his back and how his arms might fit in it. So these are the early stages of people planning things out before they actually tried to do them. It wasn't always that way. It wasn't always that you'd think before you left. Most of the time people would just leap to see what happened. So there's three things that I'm going to talk about. First, in history, there was the whole learning how to fly part. How do you fly? And there was some basic principles of airfoil design and what we call boundary layer. I'll talk about that. There was this guy Newton who invented or discovered some properties of physics. So in history, first we learned how to fly. The next thing that we did is, once we learned how to fly, we started asking questions like, what can I do with this? You know, can I carry things? Can I carry people? Can I kill people? That was a big topic. And then, can we do these things faster? Can we carry more weight? Can I travel farther? Can I kill more people? And so these sort of are the way I look at the history of flight. You know, you discovered it, you figured out what you can do with this, and then you try to figure out how to expand what you can do with it. So topic one, learn how to fly. So there's basically three reasons why inventors lived through flight experiments. One was luck. The other one was they had somebody else try the experiment. And then the other one was they started making pictures and drawings and planning, trying to see, why do things fly? Is it because they look like a bird? Because they're shaped like a bird? Does it have anything to do with birds? So here's that Leonardo thing again. But it was this guy right here, Isaac Newton, who discovered these three principles. And actually, it wasn't Isaac Newton at all, but it was somebody else with the same name. That was a joke. All right, so there's three basic principles that he discovered. Number one is that every object is in a uniform, state of uniform motion tends to remain in that state of motion unless an external force is applied to it. So if you take a block, and a brick maybe, and you put it on ice and you throw it on ice and let it go at a constant speed, basically it's going to stay at that constant speed forever unless it hits something or unless another force acts on it. So if you're not moving or you are moving at a constant speed, in order to change that speed you have to apply force. The second thing he discovered was that when there is a force, it's equal to a mass, the mass of this object, times how quickly this object is accelerating. And at this point I wanted to say that acceleration is more than just a change in speed. So if I could just say, there's this thing called velocity, which I'm sure you've heard of. And there's this other thing called speed. And the relationship between speed and velocity is that speed is something we call a scale, or it's just a number, like 50 miles an hour. Velocity is a number and a direction. We say magnitude and direction. So you could say 50 miles going north, 50 miles an hour going north, versus 50 miles an hour going south. So those two are completely different velocities because of the direction, even though they have the same speed. All right. So really, he's talking about a change in velocity. That's what acceleration is. And so I say that because you can be going 50 miles an hour north, and if you change direction to go 50 miles an hour east, you're going the same speed, but the fact that you change direction means that you've accelerated. So I want you to think of acceleration as a change in direction as well, not just speed. And then the last one is that for every action there's an equal and opposite reaction. If I push you, you push me. If I push you,